so all the elements in here, so this is U in here. This means that U is in ZP, and P does not divide P. That's what I mean. So, or rather, this is the same as ZP, ZP, deleting PZ. So I want to analyze this part. But I want to think of this like multiplicative, so the group structure is using the multiplication. That's why I write I like to write cross, because it reminds me that the group structure is multiplication. Surjective half of this map takes reduction then, which is surjective. And what I want to do is I want to get a section. Canonical way of getting a section, typical called the Teshima analysis, meaning that for any A in Z mod PZ cross, well, first of all, we know that this is a cyclic group of order P minus 1, right? The multiple group of a finite group, or whatever. Cyclic group order P minus 1. So, oh, sorry, maybe I'll put a bar here to indicate this mod P. So that means that A bar to the P minus 1 is 0 in Z mod PZ. Okay. By Lagrange theorem, every group element racing to the order of the group is the identity element. So this means that this A bar is a solution to the equation x to the P minus 1 minus 1 equals 0 modulo P. Because A bar belongs to the cyclic group, so therefore raising A bar to the P minus first power becomes an identity element, namely 1 in the multiplicative group. And therefore, in other words, this says that this A bar is a solution modulo P to the equation x to the P minus 1 minus 1. So by Hansel's law, and you can show that all the zeros of this one are exactly Z mod PZ cross, so they're different. By Hansel's law, I can find a unique A in ZP such that it's a solution to this equation, namely A to the P minus 1 equals 0, and A is congruent to A bar. So this A is called the Teichmann of A bar. Sometimes I write square bracket A bar. The relatively canonical way of writing Teichmann of like I want to make a very quick remark that if you multiply two Teichmann lifts, you get the Teichmann lift of their product. Here is why. Because the Teichmann lift is going to be what? It's going to be a solution to this equation. This equation will give you a P minus first root of unity. See? X to the P minus 1, x to the P minus 1 equals 1. So it's going to give you a P minus first root of unity. And if this is a P minus first root of unity, and that's another P minus first root of unity, so their product will also be a P minus first root of unity. And their product will be a kind of a reduction mod P will give you A bar times B bar. But then the Xiao lemma says that there's a unique such lift of this solution modulo P. So they must be equal. I can construct it either by this Xiao lemma or just taking the product. So what we're proving here is that we have a section of this map sending any A bar to its tetramer lift. And it's not any sort of map, but it's also a group homomorphism. Yes, same equation. Because see, if x satisfies this equation and y satisfies this equation, then x times y also satisfies this equation. Right. Now everything's commutative. We're safe. Right. So going this way is actually a group homomorphism. So I can actually split off. So this would imply that CP cross because without this part times the kernel of the reduction mod P. Just personally, I like to put a cross here. It doesn't mean anything to. It doesn't mean to change the set at all. It just means that we're talking about the multiplicative group constructor here. Okay. It doesn't do anything. I just really like to put a cross here, minus. So this is a nice one. So I further decompose this into a finite group, a single group over P minus 1, and that thing. It is whatever it is. And now I have to analyze this last bit here. Here's a first step into the PI analysis. I want to say that this is the same as ZP. Actually, you know what? There are two maps. Going this way, I can take the logarithm, like this, and I'll write down what it is. So some out of a loop which looks like 1 plus PA. I want to take the log. 1 over P times log. I want to normalize it. And we're going to ask, what is log? These are not real numbers, these are PI numbers. But PI number can also take log. Because it still makes sense to, the way I define this is that we all know Taylor expansion. Right? So what's the Taylor expansion of log? It's going to be PA, hopefully I can get it right. Especially when this lecture is getting video. Hopefully I get it right. The Taylor expansion of log. So what I define is just that formal power series. Excuse me, this is just formal series. And you see that the power of P on each of the terms get larger and larger. So in terms of PI norms, each of the terms will get smaller and smaller, and this will converge. And I can go the other way. So this is log going this way. And also we know that log takes multiplication to addition. And going the other way, I take exponential. Maybe I'll just write it a little left. So I have all this thing. P times B. So what's the Taylor expansion? Exponential, well, it's PB plus 2 factorial PB squared plus 3 factorial PB cubed, and keep going. And again, you see the power of P get more and more powers of P. So the corresponding term will get smaller and smaller. And this will also converge. And sort of formal arguments to say that log composed with exponential is the identity, and vice versa. To sum up, at least one piece odd, I will have QP cross. First of all, I get the valuation part, which is z, and I get the finite part. And then I get so this zp, which comes from the log and exponential. Questions? Okay.
By when was this known?
When?
By when did we know how QP cross is decomposed?
I mean, the first time I separated QP cross as z times zp cross.
No, I mean historically. Do you, I mean, you don't, I can look it up. I'm just curious.
I really have no idea.
Okay.
I think probably by the time when Hansel, I think it was probably Hansel introduced QP, and by that time he probably yes.
So I think someone was asking before, I think the question they're asking, like when we wanted to take like kinetic square root, they were asking like how do you write down, couldn't you write down a closed form solution for kinetic square root, like by doing this argument with the trinomial series, with like the exponent on that? Then you
So
can write a closed form solution for like all the coefficients of the sort of kinetic expansion.
Here's maybe a semi solution to what you're asking. So I want to get this in E7. You do the following crazy thing. Right? I mean, how do you do exponential? So what is this? This is going to be sum of binomials n, I, and actually I, right? And I do the same thing. That's okay. I'm not sure if this answers your question. No, but this n is different. Maybe I do n. And this is n. Okay, so my m is 1/2. Oh, sorry. This n. I can just formally write this. And what do I mean by this? This is, well, I mean, how do you define binomial equation? Binomial coefficients, you do, I can say 1/2 times 1/2 minus 1 dot dot 1/2 minus 1 minus 1. You can define it to be this formal quotient. And you can always show this is always, this one here is always a PI integer. And this will convert to a PI number. So it's another way of taking the square root. Did that answer the question? Or?
Yeah. But is there, sorry, maybe there's probably some faster way to see this, but with this, like, for instance, for all the, so, would this give you all the square roots? Like, if you multiplied like Z2 or something, and like looked at the places where this conversion.
So in any, I guess at least in any field, the square root is at most 2.
Yeah.
Right. So it's just plus minus.
Okay.
Plus minus. Okay, we can do that. I was actually planning on talking about it. Other questions? Or- Almost lost some time. So let's recall. So let's now get back to quaternions. What do I want to do? I want to first of all make a remark about quaternions that actually works for any field. If you take quaternion with parameters a and b, that's the same as the quaternion with where you multiply both parameters by the square of something. The isomorphism is given by sort of sending I to S times I and sending J to T times J, which is basically scale the basic parameters, and you just get that. So therefore, if you want to, so the isomorphism classes of this quaternion really just depend on, not depend on AB as, okay, I know that. I'm using something I shouldn't have erased, but I can't help. Instead of thinking about AB as an invertible element QP cross, I can think of it modulo the squares. And for, if we're dealing with rational numbers, this doesn't help too much. Rational numbers up to squares, it's just, you can parameterize them by square-free integers, but there are plenty. But for QP, it's not too bad. Because by the equation I just erased, unfortunately, what do I have? QP cross as multiplicative group is something I'm repeating. At least somehow, maybe it's sort of P odd. For P equals 2, you have to make a small error. And now if I square this group, what do I get? I get 2z plus square of whatever the thing is, and 2zp. Right? And because I assume that P is odd, so the last term, so 2 is invertible zp, so these two will be the same, so they cancel off. So when P equals 2, the last term doesn't quite cancel off, so you have an extra term. Then the first one will give you a z mod 2z. And this group is a cyclic group of order p minus 1, which is the even order. And they divide by the squares in that, so there's another z mod 2z. In some sense, if I want to know the actual most important the quaternion algebra, I just need to know A and B, where both A and B can only choose from, I guess, 4 elements. So there are basically 16 quaternions I have to look at. Some time, right? So I guess I'll talk about this next time. Yeah, I think.